Lesson: Evaluating Model Performance, Metrics, and Validation Strategies. Evaluating model performance is a cornerstone of machine learning that ensures models are reliable, accurate, and generalizable across various datasets. The efficacy of a machine learning model is not solely determined by its ability to predict outcomes on the training data, but rather its performance on unseen data. Therefore, understanding how to evaluate model performance through metrics and validation strategies is crucial for any AI professional aiming to achieve the CompTIA AI Scripting Plus certification. One of the primary metrics used for evaluating model performance is accuracy. Accuracy is the ratio of the number of correct predictions to the total number of predictions made, often expressed as a percentage. While accuracy is straightforward and intuitive for classification problems, it can be misleading, particularly in datasets with imbalanced classes. For instance, in a dataset where 95% of samples belong to one class, a model predicting the majority class for every sample would achieve 95% accuracy, but would be ineffective in identifying the minority class. Thus, alternative metrics such as precision, recall, and F1 score are often more informative. Precision measures the proportion of true positive predictions among all positive predictions, while recall indicates the proportion of true positive predictions among actual positives. The F1 score, the harmonic mean of precision and recall, provides a single metric that balances both concerns, making it especially useful in imbalanced datasets. For regression models, common evaluation metrics include mean absolute error, mean squared error, and root mean squared error. These metrics quantify the average error magnitude between predicted and actual values, with RMSE providing a higher penalty for large errors due to its squaring function. The choice between these metrics often depends on the specific problem domain and the importance of penalizing larger deviations. For example, in financial forecasting, where large deviations can be costly, RMSE might be preferred. Beyond individual metrics, validation strategies play a critical role in assessing model performance. Train-test split is a straightforward approach where the dataset is divided into separate training and testing subsets. However, this method can lead to high variance in performance estimates, particularly with small datasets. K-fold cross-validation addresses this issue by partitioning the data into K subsets or folds and training the model K times, each time using a different fold as the test set and the remaining folds as the training set. The final performance metric is averaged over all K trials, offering a more robust estimate of model performance. Leave one out cross-validation is a special case of K-fold cross-validation, where K equals the number of samples in the dataset. While OOCV provides an almost unbiased estimate of model performance, its computational cost can be prohibitive for large datasets. In practice, K is often chosen as 5 or 10, balancing the trade-off between computational efficiency and the reliability of performance estimates. Stratified K-fold cross-validation further improves this by ensuring each fold has the same class distribution as the entire dataset, which is particularly beneficial for imbalanced datasets. Real-world scenarios often present additional challenges, such as overfitting, where a model performs well on training data but poorly on unseen data. Regularization techniques, such as L1 and L2 regularization, can mitigate overfitting by adding a penalty term to the loss function, discouraging overly complex models. Cross-validation can also help detect overfitting by revealing discrepancies between training and validation performance. Practical tools and frameworks play a vital role in implementing these metrics and validation strategies effectively. For instance, scikit-learn, a popular Python library, offers a comprehensive suite of tools for model evaluation, including functions for calculating classification and regression metrics, as well as utilities for performing K-fold cross-validation and hyperparameter tuning. TensorFlow and PyTorch, widely used deep learning frameworks, provide similar capabilities for evaluating model performance on complex neural networks. These frameworks allow professionals to seamlessly integrate evaluation processes into their machine learning pipelines, ensuring that models are rigorously tested before deployment. Case studies provide valuable insights into the application of these concepts. Consider a healthcare application where a machine learning model is developed to predict patient readmission. In this scenario, precision and recall become critical metrics, as false positives could lead to unnecessary treatments, and false negatives might result in missed care opportunities. By employing stratified k-fold cross-validation and optimizing hyperparameters using grid search, the development team can ensure the model is both accurate and reliable across diverse patient demographics. Similar methodologies can be applied in other domains, such as finance, where precision in predicting fraudulent transactions is paramount, and recall is crucial for capturing all potential fraud cases. It's important to note that model evaluation is an iterative process. As new data becomes available or as the problem domain evolves, continuous monitoring and reevaluation of models are necessary to maintain their relevance and accuracy. Tools like MLflow and TensorBoard facilitate this by providing platforms for tracking model performance over time, allowing for the identification of performance degradation and the need for retraining. In conclusion, evaluating model performance through appropriate metrics and validation strategies is essential for the development of robust and reliable machine learning models. By leveraging precision, recall, F1 score, MAE, MSE, RMSE, and employing validation techniques such as k-fold cross-validation, professionals can ensure their models are not only accurate, but also generalizable to new data. Practical tools like scikit-learn, TensorFlow, and PyTorch provide the necessary infrastructure to implement these evaluations effectively, while case studies demonstrate the real-world impact of these methodologies. Ultimately, a thorough understanding of model evaluation principles is indispensable for any AI professional seeking to excel in the field and achieve the CompTIA AI Scripting Plus certification.